Okay, we're going to continue lesson 6.2, applications of trig functions. And we're going to be working with some more problems. We have here the example 5, which is height above sea level. So we have a straight road here that leads from an ocean beach at a constant upward angle of 3 degrees. And the question is, how high above sea level is the road at a point 1 mile from the beach? So here they show the figure for you. And one of the biggest problems that students have at times is what's the hypotenuse, what's the horizontal side. Sometimes those get mixed up. So here they have a picture for you. They give us show the 3 degree angle and the 580 feet. And the question is, how high above sea level is the road at that point 1 mile from the beach? And so we're going to use a trig function here. And so if we identify the things we know, we have the 5,280 feet. That represents the hypotenuse. And we're trying to find the height, which would be the opposite. So we are going to do the sine. So we say the sine of 3 degrees is equal to the opposite, which would be h, over 5,280. And then it's just a matter of multiplying both sides by 5,280. And let's see, I gotta get my calculator out. Didn't do that yet, so we'll bring our calculator up. And we'll check our mode. Remember, every day you should always check your mode, or every time you turn it back on, just make sure you're in the right mode here. So 5,280 times the sine of 3, and that would be 276.33 feet. So the height is approximately 276.33. And don't forget, here's a problem with units, and so make sure you include your units in your answer. Okay, we're going to look at example 6 here. This has 2 parts to it. It says ladder safety. So according to the safety sticker on a 20-foot ladder, the distance from the bottom of the ladder to the base of the wall on which it leans should be 1/4 of the length of the ladder. So in this case, that would be 5 feet. Letter A, how high up the wall will the ladder reach? And letter B, if the ladder is in this position, what angle does it make with the ground? So we need to draw a triangle here, and so we'll go ahead and this will be a right triangle. So we'll say that it look like this. Oops, that's not the one I want. So get rid of that one. And let's try this one here. Come on. No. Well, all right. I'm going to draw it instead, I guess. So we have, here's our wall. Here's our ladder, which is 20 feet. And then this distance here is going to be 5 feet. So we've got the ladder, which is 20 feet. Don't forget the ladder is always the hypotenuse of our right triangle. And it should be 5 feet away from the wall, since that's 1/4. And we want to find out how high up the wall the ladder reaches, so we want to find the height. So this would be a Pythagorean theorem question. So 5 squared plus h squared equals 20 squared. So we subtract 5 squared from both sides, we get 375. Okay, that would be 400 minus 25. So the height of the up the wall, this should be then, would be the square root of 375, which is approximately 19.36 feet. So that's almost as high as the ladder. And the next question is, if the ladder is in this position, what angle does it make with the ground? And so we'll use, we want to find this angle here, theta. And so we're going to use cosine in this case, because we know the adjacent side of 5 and the hypotenuse of 20. So to find that angle then, we're going to do the inverse cosine. Okay, whenever we're trying to find a ratio, we do sine, cosine, or tangent. whenever we're trying to find the angle, we're going to do the inverse cosine of that ratio. So this angle is going to approximately be, so we do second cosine of 5 divided by 20, or you could use 1/4, and that's approximately 75.52 degrees. And like I said, once again, don't forget your units when you're doing these problems. Okay, we're going to look at example 7. This is an indirect measurement problem. It says the question here is a flagpole casts a 60-foot shadow when the angle of elevation of the sun is 35 degrees as shown in the figure. Find the height of the flagpole. Okay. So we need to look at, once again, which trig function are we using, so which parts do we know? So in this case here, if our 35-degree angle is here, then this is the adjacent side, and the height here would be the opposite. And so we're going to use tangent then to find that height. So we would have the tangent of 35 degrees is equal to the opposite, which is h, over the adjacent, which is 60. So then we just multiply both sides by 60. And so 60 times the tangent of 35 is 42.01. So it's approximately 42.01 feet for the height of the flagpole. Yeah, let me write that a little bit better. Okay, here we're going to look at example 8. This is on indirect measurement. Wire needs to reach from the top of a building to a point on the ground. The building is 10 meters tall, and the angle of depression from the top of the building to the point on the ground is 22 degrees. How long should the wire be? So let's draw our picture. So we've got a building here, and it says the wire needs to reach from the top of the building to a point on the ground. So here's their point on the ground. And it says the building is 10 meters tall. So we got 10 meters here. And it says the angle of depression from the top of the building to the point on the ground is 22 degrees. And so that means that, and I'm going to need to change my picture a little bit here. So let's extend this a little bit. And extend this. Okay. When it's talking about angle of depression is this angle here. So if that angle there is 22 degrees, then that means that this angle here is 22 degrees. So when we look out and down, we're talking about depression. So if I'm up at the top here and I look out across from the top of the building down to the ground, then I'm talking about depression. If I started down at the ground where that point is, down here, and I look up at the top of the building, that's called angle of elevation. So the interesting thing about it is those two things happen to be the same. So we could actually look at our triangle. We could do it two different ways. We could use this triangle here that I draw, which is a pretty rough triangle, where this would be 10, and either way we're trying to find the length of the wire. I'll call that W. So, you know, you have two triangles that are exactly the same, just in different spots, and basically depends on how you want to work with that one. But the angle of depression, looking out and down, the angle of elevation, looking out and up. And either way, we're talking about trying to find the hypotenuse in this situation, and we know the 10 meter side, that is going to be the opposite. So that would be the sine we're going to use of 22 is going to be the opposite 10 over the hypotenuse W. Now here's a problem we haven't seen before where the variable's in the denominator. So the first thing you've got to do is get it out of the denominator. So we're going to multiply both sides by W. And then, so we'll rewrite our equation. And then we're going to divide by the sine of 22. So the length of the wire is approximately 10 divided by the sine of 22, which is about 266.95 meters. So that's quite a long wire. 266.95 meters. Okay? Pretty long wire they have there. All right, so what the difference in this problem is that we're talking about elevation and depression, and make sure you know which angle that is we're talking about, and then if you have your variable in the denominator, working with that. Okay, so we're going to do example 9, which also involves indirect measurement. Here it says a person on the edge of a canal observed a lamp post on the other side of with an angle of elevation of 12 degrees to the top of the lamp post and an angle of depression of 7 degrees to the bottom of the lamp post from eye level. The person's eye level is 152 centimeters. So we want to find the width of the canal, and we want to find the height of the lamp post. Now in this problem, we have to find the width of the canal first, because we're going to need to know this here. We're going to need to know that side there, so we'll use W for width. And before we can actually find the height of the lamp post. Okay? So in doing this, we know that this side right here of the lamp post, this part of it, is going to be 152, because it is the same height as the man's eye level. So to be able to find the width then of the water, we are going to do, we know the opposite side from the 7-degree angle is 152, and adjacent is W, so we'll have tangent. So the tangent of 7 is equal to the opposite, 152, over the adjacent, which is W. And so here we've got that situation again with the variable in the denominator, so we'll multiply by it. So we get W tangent of 7 equals 152, and then divide by the tangent of 7. So W then is approximately, and take our calculator, so move it over this side for a moment, and we get 152 divided by the tangent of 7, which gives us 1,237.94 centimeters. Okay, let's see. Okay, so we're talking about centimeters here. So 1,237.94 is how wide the canal is. All right, so here we go, 1,237.94 centimeters. Okay, and then we need to find the height of the lamp post. So now we need to find, we'll call this X here, and that would be this height of the lamp post here, this part of it, and then we can add that to the 152 to find the total height. So we need to find X. We know that the 12-degree angle here, and we know the width of the canal, so that would be the adjacent side, and we're trying to find the opposite. So we've got the tangent of 12 degrees is equal to the opposite, which we don't know. We'll call that X, and the width is 1,237.94. Right? So we'll multiply by 1,237.94. So X then would be approximately, and back to our calculator, and here. So we have 1,237.94 times the tangent of 12, and we get 263.13 centimeters. 263.13. So then to find the height of the lamp post, I have to add 152 centimeters to that. So that would give us 0.13, 5, 1, and 415. So the height of the lamppost would be 415.13 centimeters. And let's see. All right, and they weren't asking for feet, so we're good with our centimeters. We could convert it if we wanted to, but we're good there. So that is all of the examples for applications of trig functions.